Volume. So I just want to let everyone know that that last integral we did in class on Friday was accidentally terrible. It really should have been around the better axis to revolve around, not the more terrible one. So hopefully you didn't spend time worrying about that too much because it was awful. Let's look at these two examples. So we're going to talk a bit about volumes of revolution, which was the kind of volumes we've been doing, and then we'll talk about a few other ones where it's volumes by cross sections, which are less nice, in my opinion. So let's say we want to find the following. We want to find the volume of the solid generated by revolving the region bounded by, oh my God, so many words. Y equals 2 over x, x equals 0, y equals 1/2, y equals 1 around the y-axis. And every time you do a problem like this where you're revolving around an axis, I recommend you draw the region. You don't have to draw the volume. You definitely should draw the two-dimensional region that you're going to revolve around, whichever axis you're revolving around. So let's see here. I know that 2 over x looks vaguely like this. Doesn't have to be a perfect picture. X equals 0 is my y-axis, so that right there. Y equals 1/2 is a horizontal line. And y equals 1 is a higher horizontal line. And then I'm looking for the region that is bounded by all 1, 2, 3, 4 of those curves. So it's this little section in here. Bounded above by y equals 1, below by y equals 1/2, on the left by x equals 0, on the right by y equals 2 over x. It is also worthwhile to find these points of intersection here. Sometimes you don't actually really need them at all. In this problem, we actually probably, no, I don't think we actually need them, but we're going to find them anyway. So this is the curve y equals 2 over x. I think it's relatively straightforward to see that if y equals 1, x is going to be 2. And if y equals 1/2, x is going to have to be 4. You can also set things equal to each other and solve for x, but right, if you're setting 2 over x equal to 1, I think you can see pretty quickly that x has to be 2. And similarly, if 2 over x equals 1/2, then x has to be 4. There's no other way around it. All right. We're revolving around the y-axis. Okay, so a question people have asked me a couple of times is, how do you know if you're using disk or washer method? And really what I would really say is they're the same. I know they're a little bit different, but technically the disk method is just like the degenerate version of the washer method. The washer method is all inclusive, and the disk method is the special case where the inner radius is 0. But from a picture point of view, we know we're using the washer method if you have space between your axis of rotation and your region. And we're using the disk method if your region is flush with your axis of rotation. Or one other way to say it is, if your region is bounded by the axis of rotation as one of its boundaries, then it's going to be the disk method. And here, the y-axis, which is also the line, x equals 0, is one of our boundaries. So we know we're using the disk method. Great. So we're going around the y-axis. We should draw a little strip that is perpendicular to our axis of rotation. And we're imagining, again, you don't really have to draw this. We're imagining that getting revolved around and creating a disk. And the volume of this disk is pi times the radius squared times the thickness, which is a small change in y. And if you're going around a vertical axis, it's always going to be in terms of y. If you're going around a horizontal axis, it's always going to be in terms of x. I should say, if you're rotating around a vertical axis, it's always going to be in terms of y. If you're rotating around a horizontal axis, it's always going to be in terms of x. That is not a statement that would be true in the 21 series because you have other methods available to you, but it is definitely a statement that is true in the 17 series because we only use this class washer method, which is great. Okay, so I need to know what the radius is, and typically the radius is just the function. So here our radius is going to be the function that we're touching when we are looking at the right side of this little strip. And unfortunately for us, that function is written in terms of x, which it usually is. So we're going to take our function y equal to 2 over x, and we're going to solve for x. So x times y equals 2. So x equals 2 over y. I don't love this example because the reverse or the inverse function looks like it's exactly the same, and it kind of is. That doesn't usually happen, but it does happen here. So don't fool yourself into thinking that if it was like y equals e to the x, that you would just change them and get x equals e to the y. No, you would get x equals natural log of y. So just be careful. So that's our radius. How far away we are from the y-axis. So our volume of our disk is going to be pi times 2 over y squared dy. And the variable here in your function better match your d whatever, your differential variable. Then our total volume, we're just quote unquote adding up all the volumes of all the disks. So we're going to let the disks go as low as y equals 1/2, as high as y equals 1. Or in other words, we're going to integrate from 1/2 to 1 of pi times 2 over y squared dy. The rest of this is less terrible in my opinion. Like the setup is the hard part for these usually. The integration is often pretty straightforward. Not always. Sometimes it's some terrible integration by parts or something. But in this case, we can say that we're going to bring out the pi and the 4, because 2 squared is 4, and get 4 pi times the integral from 1/2 to 1 of y to the negative second, which is this, or I should say 1 over y squared, which is the same as y to the negative second. We integrate. We get y to the negative first over negative 1 from 1/2 to 1. We plug in and we get 1 to the negative 1 over negative 1, which is negative 1, minus 1/2 to the negative 1, which is 2 over negative 1, which is minus 2. So we get 4 pi times 1, which is 4 pi. I would have probably done something a little bit different here and just rewritten this as negative 1 over y, so that when I plugged in 1, I got minus 1. When I plugged in 1/2, I got minus 2, or minus 2. Cool. Yes.
So usually, typically, you always do the find the inverse of the original.
So no, but it depends. If I'm going around the x-axis, I want y as a function of x. Or I should say I require y as a function of x. If I'm going around the x-axis, sorry, I said the wrong thing there. If I'm going around the x-axis, y has to be a function of x. If I'm going around the y-axis, x has to be a function of y. So in this case, since I was going around the y-axis, I had to get x as a function of y. In the next problem, which is very similar, you have completely different results. Other questions about this before I move on to the next one? Yeah. Whatever your length measurement was cubed. So if our units were measured in centimeters, the volume would be in centimeters cubed. Let's look at the next similar problem, but very different in execution. So I'm just going to write the bounds and the axis. So here are boundaries boundaries, sure, why not? Our boundaries are the functions y equal to 9 over x equal to 0, y equal to 3, why would you pick that? I'm going to pick y equal to 9. The problem said y equal to 8, but that's trash. Pick y equal to 9. And then we're going to go around the x-axis. So although it's not exactly the same, it's pretty much the same picture. Like, yeah, I know the values are different, but it's still a function that's something times 1 over x. Great. Here's my 9 over x function looking pretty much the same as 2 over x. And then I've got x equals 0, which is still the y-axis. I've got y equals 3, which is still some horizontal line. Ooh, horizontal, James. Okay. And I've got y equals 9, which is some higher horizontal line. So I've still got a region that's flush with the y-axis. But now the issue is we're not rotating around the y-axis, we're rotating around the x-axis. This is doubly terrible because we're going to have to use two integrals. Because if I draw a little strip here, the outer radius is y equals 9. The inner radius is y equals 3. If I draw a strip over here, and again, I'm always drawing my strip perpendicular to my axis of rotation. Oh, someone's trying to get in here. So this is Dorfield thing. No. All right, sounds like someone's trying to get in. If you draw a strip over here, your outer radius is a different function. It's y equals 9 over x. Your inner radius is still y over 3. So if either of your radii change, either the outer one or the inner one, as you move across your region, that means you have to use more than one integral, which is a bummer. Oh well, that's what we've got. This would be great if we had a different method of integration, but we don't. So oh well. So two integrals. The first integral. Actually, before I get going here, I should find these points of intersection. So here I've got y equals 9 intersecting y equals 9 over x. So if I set those equal to each other, everyone's able to show me on their fingers what the answer to this equation is. Yes, exactly that many. X has to be 1. You don't need to show the work of solving this. Everyone's going to be cool with you just knowing that, oh yeah, if I plug in 1, I'm going to get the solution here. Similarly, if I find this point of intersection over here, I can see that if I set 9 over x equal to 3, x is going to have to be 3. So I'm going to have two integrals. The first one from 0 to 1, I'm going to have pi times my outer radius is the function that's further from the axis of rotation, which is y equal to 9 squared, minus my inner radius, which is the function closer, which is 3 squared. Just want to point out, this is my pi times big R squared minus little r squared, and then we're just integrating the whole thing. Same deal for the next piece. But now we're going to go from x equals 1 to x equals 3 also. Yeah, sorry. Get the label things here. And that's, yeah, 3 comma 3. So here we're going to go from 1 to 3. And again, pi times my outer radius, which is now the function further away, which is 9 over x squared, minus my inner radius squared, which is still x equal to y equal to 3. And then we're squaring it. Both of these are just washer method integrals. And we did have to use the washer method because our region was not flush with our axis of rotation, right? There's definitely space between the region we're rotating and the axis we're rotating it around. Questions about this setup? Yeah. Well, so it depends on the region. So this region, or a region like it, like in the previous problem, revolved around the y-axis, didn't require two integrals. Because so the thing I really want you to take to heart is drawing this vertical strip that is perpendicular to your axis of rotation. So in the previous problem, it didn't matter where I drew the strip. Let me zoom in for a minute here. It didn't matter how high or how low I drew that little strip. It always would have had x equals 0 as its left boundary and x equals 2 over y as its right boundary. Doesn't matter, right? Draw it at the top, draw it at the bottom, somewhere in between. Left boundary is always going to be x equals 0. Right boundary is always going to be x equals y, 2 over y. On the other hand, for this new example, which is essentially the same region revolved around the x-axis, now it matters where I draw my strip. if I draw it way to the left, well, then the outer boundary, or the top function, I should say, the further away function is y equals 9, and the closer function is y equals 3. But if I shift my strip further right, further than x equal to 1, one of those boundaries changes. Now the top function is no longer y equals 9. The top function is y equals 9 over x. That means we have a different outer radius, which means we have to do a different integral. So that's really the deciding piece of information. That's why I would encourage all of you to draw the region and then draw a strip perpendicular to the axis of rotation. And if you find yourself having to draw different strips because your top and bottom change midway through, that means every different strip needs a different integral. Whereas in the previous one, right, I could have drawn different strips here, and no matter where I drew them, it's always the same right and left. That clarify things, I think? I hope. Okay. The rest of this problem, I almost want to just skip, but I won't. But here's the rest, which isn't too terrible. 81 minus 9 is 72. So you've got pi times the integral from 0 to 1 of 72 dx plus pi times the integral from 1 to 3. Let's write this as 9x to the negative second minus 9, which is not that bad. I feel like all of you should just say the integral from 0 to 1 of 72 is 72, right? 72x from 0 to 1, which is 72 minus 0. So we're going to get 72 pi plus pi times integrating that, we get negative 9x to the negative 1 minus 9x from 1 to 3. In this case, I would do a little bit of modification before I plug things in here. I'm going to write this as pi times, no, that's good. I'm going to write it as negative 9 over x minus 9x. If I was being smarter about it, I would have factored out negative 9, but I forgot to. Then we're going to plug in the numbers. We're going to get 72 pi plus pi times negative 9 over 3 is negative 3. Negative 9 times 3 is negative 27. Minus, getting a little tight here. Plug in 1, negative 9 over 1 is negative 9. Minus 9 times 1 is also 9. Sorry, that's a little bit gross. Apologies. So you get negative 40 plus 18, which is 22. Negative 22. So we're getting 72 pi minus 22 pi, which is 50 pi. Okay. As long as the answer is not negative, I'm happy with what I've got. I don't think I made a mistake anywhere. You are also welcome to ask me if you have a question. I don't mind answering questions. Yeah.
Why don't we split from like 0 to 1, which is like 9 squared minus 3 squared, and then have like the other side of 9 over x minus 3 squared?
So the reason for that is because from 0 to 1, we're rotating this shape around the x-axis. So like if I actually draw the picture over here, this shape gets rotated around, and we've got this kind of heinous looking thing like that. So from 0 to 1, my outer radius is always 9, my inner radius is always 1. So I've got this, pi times 9 squared minus pi times 1 squared, which is giving me, right, pi times, brain, James. No, yeah, oh yeah, sorry, that's a 3, not a 1, sorry. Pi times 9 squared minus pi times 3 squared. But then for the second part here, then we do this. We dip down like that, and now we're rotating something that looks like where my outer radius is now this 9 over x function. It's no longer just y equals 9. And my inner radius is still y equals 3. So that's why from 0 to 1, I need my outer radius to be 9, my inner radius to be 3. But from 1 to 3, I need my outer radius to be the function 9 over x, and my inner radius to be still 3. That's why we're changing it here. And again, the way I'm encouraging you all to see that is by drawing the vertical strip, or I should say the strip perpendicular to the axis of rotation, to see if you need more than one integral. Most of the time, you will only need one integral to do this, but occasionally it's terrible and you need two. All right. Other questions? Yeah. Mhm. Oh, you're right. I made a mistake. What did I miss? So I rewrote it as 9 times x to the negative second, but I squared the x and brought it up, but I didn't square the 9. Should have been 81 x to the negative second. Good call. What happens when you go too fast? So that should be an 81 there. Ugh. That should be an 81 here. Gross. That should be an 81 here. Awful. And then when you plug it in, blah. Negative 81 over 3 is negative 27. Boo. Negative 9 times 3 is also negative 27. Great. And then when you plug in 1, you're going to get negative 81 over 1, so negative 81. Ugh. Minus 9. So really this is negative 54 plus 90, which is 36. And it's adding 36, not subtracting 36. So sorry about that. Apologies for the mistake. That should be 72 pi plus 36 pi, which is 108 pi. Good catch there. Thank you. Yes, don't hesitate to call me out. I occasionally do make mistakes. I'm not afraid to admit it. I'm just a casualty of going too fast sometimes. All right. Other questions, comments, concerns? Yeah. Yep. Right, because the inner, right, because exactly, because if you rotate the shape around, you always have this hole. You're essentially like just like kind of thinking of like drilling a hole of radius 3 out of this solid shape. Yeah. Should we do another one? It's okay. Another one with 2 integrals? Fine. Okay. Now I have to make something up. Oh, do I have examples here? I do. Let's see. What's sure, I like that one. Yeah, let's do this terrible thing. All right. So let's say we have the following region. So our region is, yes, I can. So our region is bounded by y equals x squared, x equals 0, and y equals x plus 2. And first things first, we're going to revolve around the x-axis. Draw the region. It doesn't have to be perfect. It has to be good enough. So here's a common issue that occurs when people write problems and aren't careful. Technically, there's 2 valid regions here because there's one region in the first quadrant bounded by x equals 0, y equals x squared, and y equals x plus 2. There's also this region over here in quadrant 2 that's bounded by x equals 0, y equals x squared, and y equals x plus 2. So usually people will clarify, which I meant to do, and say the region bounded by these things in quadrant 1, which is the typical choice. Although you could just as easily put quadrant 2. But I won't, because quadrant 1's more interesting. All right, so if I draw a vertical strip, is it possible to draw a vertical strip that has 2 different tops or 2, like, if I draw my vertical strip in here, is there any way I'm getting anything other than x plus 2 is the top and x squared is the bottom? No, not possible. I'm always fortunately stuck with those bounds. So here the setup for this integral Shouldn't be too terrible. Oh, I should ask another question. Give me a thumbs up if I'm using the disk method, a thumbs down if I'm using the washer method. I think it's got to, I mean, technically, I know I said they're both the same, but okay. It's definitely the washer method because my region isn't flush with my axis of rotation. My axis of rotation, I know I didn't label it. There's my x-axis, there's my y-axis. I'm going around the x-axis, which is not the same as the line x equals 0, right? There's x equals 0. There's the x-axis, which is y equals 0. Okay, so this is the fortunate situation. Our volume here is going to be, I should say, I like to say the volume of my washer is pi times my large radius squared minus my small radius squared times d what? Dx in this case, because my vertical strip has a thickness that's just a little bit change in x. And then we're going to actually fill in our radii. The larger radius is the function further away from the axis. The smaller radius is the one that's closer. Which might feel slightly, what's the word I'm looking for? When something doesn't fit what you think is going to happen. Thank you so much. But might feel slightly counterintuitive because often we feel like the function that has the higher degree should be the bigger one. And eventually it will be, but not between whatever the bounds are here. So yeah, x squared is the smaller function or the one closer to the axis of rotation. X plus 2 is the bigger one, the one further away. There's something else I wanted to say here. No, I guess not. Okay. So then the total volume is going to be the integral of x plus 2 squared minus x squared squared. And then we put the pi out in front. And then we should have probably thought about the limits of integration earlier. If we set these two things equal to each other, we can find them either by guessing. Well, you don't have to guess here. You can bring everything to one side and factor and see that your points of intersection are x equal to 2, which is the point here, 2 comma 4, and x equal to -1, which is the point here that we're not really worried about, -1 comma 1. So it looks like our limits of integration should be as far left as 0 and as far right as +2. I don't want to do the rest. But here's the rest. So then we multiply it out. You'd have x squared plus 4x plus 4 minus x to the 4th. You would anti-differentiate. You would have x cubed over 3 plus 2x squared plus 4x minus x to the 5th over 5 from 0 to 2. And then if you're taking a test, you just plug it in and you stop. You get 8/3 plus 2 times 4 plus 4 times 2 minus 32 over 5. Check to make sure that when you plug in 0, they're all 0. Yep, they are. So don't even write anything down and stop right there. Don't do more unless you are compelled to. You've done everything else on the exam that you can. I should ask, have any of you been asked to find volumes of regions rotated around other axes? Like around the line y equals 7 or around line x equals 5? Great. If you do, let me know. We'll talk about it. But if you don't, it's just one more thing to think about, but it's not that much harder. I mean, if you don't have to do it, then we shouldn't do it. I mean, I don't generally feel that way about life. But like math, if you don't have to do the thing, you should just not worry about it until you have to. Okay, let's take the same region and revolve it around the y-axis. I guess I'll have to draw it again. All right, so there's our region revolving around the y-axis now. And in this case, depending on where we draw our perpendicular strip, if I draw it here, I get to use the disk method because my inner radius is 0 and my outer radius is the further away function. But if I draw my strip here, I have to use the washer method. And my inner radius is now the line and my outer radius is now the parabola. Okay. So we're going to break it up here at y equals 2. That's our kind of boundary. So the lower half is probably misleading. The lower portion is going to be the disk method. And the volume is going to be, well, the volume of one of these things rotated around. Oh gosh, that's okay. It's going to be, pi times my radius squared times dy. Why dy? Because again, this thickness is a small change in y. You've moved up or down a little bit, not left or right with the thickness. Yeah, that says disk, by the way, in case you couldn't tell. I was like, what did I write there? Oh, disk. Okay. So I'll point out this integral is going to be in terms of which variable? Y. So that means your functions have to be in terms of y. So we can't have, which I didn't write down, y equals x squared or y equals x plus 2. We have to isolate x and have x as a function of y. So y equals x squared becomes x equal to what? Well, technically, if I was being super extra careful, it'd be plus or minus the square root of y. And if we were in quadrant 2 on the left, we'd actually have to use x equal to the negative square root of y because on the left side, x is negative. On the right side, though, x is positive, so we should use x equal to the positive square root of y. Just be careful, though. When you have a function that like breaks apart into two pieces like that, you do have to be careful about which piece you're using where. So we're going to use the positive square root for our outer radius. So that's just going to be pi times the square root of y squared dy. And then the total volume for this portion is going to be the integral from y being as low as 0 to as high as 2. Pi times the square root of y squared, which is pretty straightforward, right? This is a nice thing, right? You're just integrating y. So pi integral from 0 to 2 of y dy. You get pi times y squared over 2 from 0 to 2, and that's going to be pi times 2. So the lower half is just fine, or the lower portion. The upper portion is a little bit more work, but really not that much more work. It's still the same, all of these volumes of revolution, it's the same idea every time. You're maybe having a disk, maybe having a washer, but you're always just doing pi times the radius squared, maybe minus pi times the smaller radius squared, and then integrating the whole thing. So for the upper portion, my outer radius is going to be x equal to the square root of y. And that's my further away function. And my inner radius is going to be x equal to y minus 2. Right? Because if I take this one here and solve for x, you get y minus 2 equal to x. And then we do the usual thing. The volume is going to be the integral of pi times your outer radius squared minus your inner radius squared dy from a low y value of 2 to a high y value of 4. Then we actually write it out. So our large radius is the square root of y. Our small radius is y minus 2. Also, just by the way, kind of interesting that depending on the orientation, right, in the previous problem, the closer function to the x-axis was y equals x squared, and the further away function was the line, and now they've kind of switched roles. Around the y-axis, the closer function is the line, and the further away function is the parabola. That happens a lot, actually. So simplifying, we get the integral from 2 to 4 of y minus y squared minus 4y plus 4. I would take the minute to simplify this even further and say it's the integral from 2 to 4 of negative y squared plus 5y minus 4. I do think it is almost always worthwhile to simplify before you integrate. After you integrate, but before, sure. So we get negative y cubed over 3 plus 5y squared over 2 minus 4y from 2 to 4, and then you plug in and you just stop there. You get negative 64 over 3 plus 5 times 16 is 80 over 2 is 40 minus 16 minus, and you plug in 2 and you get negative 8 thirds 5 times 4 over 2 is 10, and then minus 8. And then you don't touch it. Oh, except you do touch it, because then you say it's this plus that. So your final answer is 2 pi plus that. It's gross. They're all gross. I should just stop saying they're gross. They're all gross. Except for the few times they're nice. All right. So not to move too quickly, but who am I kidding? We should talk about some of the other types of volume questions. Some of these cross-section things where you've got a region in the XY plane and cross-sections parallel to, or sorry, perpendicular to one of the axes are triangles or squares or circles or semicircles, or that's about it really. So yeah, sorry, I know, I want to get to at least one, maybe two. Yeah, let's look at, I don't love that one. Sure, let's look at this one. So let's say, so I hate the phrasing here. I'm just going to say it the way I want to say it. So the region in the XY plane is bounded by the parabola y equal to 9 minus x squared and the line y equal to 0. Let's make life easy. And then, yeah, we'll do it that way. Cross sections cut perpendicular to the y-axis are squares whose side length lies in the region. I'm sorry, the phrasing here, I'm bad at writing. I apologize for my writing here. It lies in the parabola. I'll draw the picture, it'll make more sense. Sorry, I know my phrasing here is never good. So here's what I mean by this. You've got some parabola, some region bounded by a parabola and the x-axis, which is y equals 0. So your region looks like this. And then what we're saying is that if you cut this region perpendicular to the y-axis, so we're cutting it across like this, then that part there that lays in the region is the side of a square that's shooting up into the third dimension, out like up out of the page. So like if my parabola is just sitting on the table here like this, and I pretend that's a parabola, then here is my square popping up out of it, like that. And our job is to find the volume of all of these squares added up together that have different bases depending on where in the parabola they're sitting. I generally tend to like to draw a picture like this. That's my y-axis, not my x-axis. There's my x-axis. So here's my parabola. Again, this picture is not necessary, except it helps us kind of see what's happening. So there's my parabola again, sitting on like the ground. And then here's my cross section. And here's the square that's shooting up out of it. And so we're taking all of these squares and really we're imagining that they have a little bit of thickness. And we're finding their volumes and we're adding it all up. So that's the idea here. So just like the previous things we've done, we're going to start by finding the volume of a slice, right? It's like a weird loaf of bread. And we're taking slices and we want to say how much volume does this one slice have? And then we're going to add up all the volumes to find this total volume. Okay, so how do I like to do this usually? Yeah, so usually I start with the following. Whatever this length is here, I'm going to start by calling it L. And sometimes the area of your region is easy, like in this case. So if this side length here, sorry, yeah. So if I just pick this square here and say, okay, great, that square there with a little bit of thickness, if it has a side length of L, then the volume of my slice is going to be L squared times dy in this case. It's dy because my cross sections are perpendicular to the y-axis. Maybe I chose poorly. Not really. I think dy is just fine. Okay, so there's the volume of a slice. But what's my differential variable? What's the differential? It's the D thing. D whatever, that's your differential. So here my variable is definitely Y. It means I better be having a thing I'm integrating in terms of Y, bless you. So I need to get that length in terms of the variable I actually want to use, which is Y. So that's when we go back to this picture and say, okay, well, shoot. I'm gonna draw it again. So I'm really interested in figuring out what this length is here, from there to there. So, I know this function is y equal to 9 minus x squared. I want things in terms of y, which means I better solve for x in terms of y. So what I really want to have here is x squared equals 9 minus y, x equal to plus or minus the square root of 9 minus y. The right-hand point is the positive square root of 9 minus y, comma y. The left-hand point is the negative square root of 9 minus y, comma y. So for example, if y was 2, this point would be 2 comma root 5, and this point would be, sorry, it'd be root 5 comma 2, apologies, because the x part comes first. And this right here would be negative root 5 comma 2. And the distance between them would be root 5 minus negative root 5. Or more generally, my length is going to be the right x coordinate minus the left x coordinate, which ends up just being 2 times the square root of 9 minus y. And then the volume of my slice is going to be that thing squared, which almost always comes out nice. Like most of the time, it looks like it's going to be terrible, but then you end up you can't almost help yourself but square it, because whether it's a square or a circle or a triangle, you've got one dimension times another dimension, which almost always gets rid of whatever square roots are there. So most of the time, these integrals are not too terrible. That ends up equaling 4 times 9 minus y. And then, oh, sorry, don't forget the dy. And then we're going to do the integral to find the total volume. It's going to be the integral from, well, my y values go as low as 0, as high as, if that's a 9, of 4 times 9 minus y dy. The setup is terrible, but the actual integral, that's blanket statement for most of these volume questions. The setup is usually terrible. The actual integral is usually not that bad. I don't think I need to do that one. You'll do that. We should save these. We should use these last 5 minutes to set up another one. Or I should say, address any questions about this one before I set up one more. See, I had a region in mind. Yeah, let's do that. Okay. One more. Yeah, one more. One more setup. So, the region is a circle. Circle with radius, take your pick. 7. That's a poor choice, whatever. Circle with radius 7 and cross sections. Doesn't matter which axis you pick, because circles have symmetry in all the good ways. So you pick cross sections perpendicular to the x or the y axis. If you get a choice, I would pick the x axis. Are what kind of terrible shapes can we come up with? Squares are too easy. One choice would be semicircles. So essentially, we're going to get a hemisphere, right? Because we have a circle as our base region, and then we're saying that cross sections are themselves semicircles. Okay, so here's how I'm going to start. There's my region. Excuse me. Radius of 7. And here is my, I would generally pick a cross section perpendicular to the x-axis. So here's my cross section. That's the base of my semicircle. So, right, this here is that there. Those are the same, just a different perspective. And what do I like to call that? I like to call that L. So this length is L. And then I want to find the area of my little cross-section thing. So it's a semicircle. Ooh, maybe I shouldn't have called it L. No, it's fine to call it L. So my cross-section, well, it's a semicircle, and the area of a semicircle is 1/2, because it's half of the area of a circle, pi times my radius squared. But in this case, my radius is L divided by 2. Because L is acting like my diameter of this semicircle. This is really 1/2 pi times L over 2 squared. Great. Oh, I forgot a very important thing. I forgot the dx. Because really it's like this, the small change in x there. And then that's where I then go over here and say, okay, well, now I actually need to find L in terms of x. Fortunately, we know the equation of the circle. It's x squared plus y squared equals 49. So then solving for y is equal to plus or minus the square root of 49 minus x squared. So then you have the top minus, and the top part's the plus part, the bottom part's the negative part. So we have that L is equal to 2 times the square root of 49 minus x squared. And I'll say that again because I know I said it kind of fast. The top half is y equal to plus the square root of 49 minus x squared. The bottom half is equal to y equal to the negative square root of 49 minus x squared. So then the area of our semicircle, okay, we're fine, is 1/2 pi times this length divided by 2 squared. How nice. And then to find the total volume, and I probably should have been saying volume of a slice, but I wrote area. Sorry. The total volume is going to be the integral from -7 to 7 of this thing here. Which should end up being half the volume of a sphere of radius 7. So do some work, check for yourself. This should be 1/2 times 4/3 pi times 7 cubed. Because the volume of the sphere is 4/3 pi r cubed, and this is half of that. And I'm out of time.